It's a pleasure to have Will Perkins from University of Illinois Chicago to talk at our seminar. Will is working on questions in between combinatorics, statistical physics, and some computer science applications. He does very interesting work, and I hope he will share some of it on the interface of the combinatorics and statistical physics, as far as I understand, on counting independent sets with cluster expansion today. So, thank you. Please.
Great. Well, thank you very much. Thank you, everyone, for attending. I hope everyone's doing well. Please do, as we go, ask any questions you have in the chat. I have the chat open on my screen, so if you have any questions at any time, please do ask that. You know, I'll talk for like 55 minutes, and then after the talk, if anyone wants to stick around and ask more detailed questions, I'm happy to chat afterwards. But what I'm going to talk about today, I'm going to try to explain how you can use some classical technique in statistical physics in combinatorics, and in particular counting independent sets. And the particular paper this is based on is joint work with Matthew Jenssen, but I'll mention some other co-authors as I go. Okay, so the one thing I'm quite interested in that statistical physicists have, how can we use this to solve problems in, say, combinatorics or computer science? And the first part of the talk, I'll try to give you a very, very high-level overview of what I mean by this intuition. And then I'll focus a lot on one particular tool that they use. And that particular tool is something called the cluster expansion. And I want to show you that it can be a very useful and very versatile tool for enumeration. And so that's the main plan of the talk. I really want to focus more on explaining this particular method than on any certain results, but we'll have some results to motivate us. Okay, so statistical physics. What is statistical physics? So at a very high level, it's the idea that you can model some physical material, maybe like a gas or a magnet, as a random assignment of spins, or let's say colors, to the vertices of some graph. And so here we have some section of Z2, the two-dimensional lattice with nearest neighbor edges, and the spins are, say, pink and light blue. And a statistical physics model is just a probability distribution on these spin configurations that's really determined by local interactions. So the spins interact across edges just with their nearest neighbors, but this local interaction, this simple local interaction, can actually lead to very complex and interesting global phenomenon. And that's what I want to get across. So just for the purposes of this discussion, let's talk about maybe the one of the most classical statistical physics models, the Ising model. This is a two-spin model, plus one and minus one spins. You can think pink and blue in the last picture. And we have to describe what is this probability distribution. And this probability distribution, well, to a certain assignment sigma of plus minus one spins to the graph, the probability you see this assignment is proportional to the exponential of beta times the sum over edges of sigma u, sigma v. Okay, so sigma u, sigma v, these are plus minus one spins. So this is 1 if the spins agree and minus 1 if they disagree. And so if, let's say, beta is greater than 0, then we prefer agreeing spins across an edge. Okay, so and we would say the model is ferromagnetic. And then to make it a probability distribution, we have to divide by a constant that makes the probability sum to 1. And this is this ZG of beta. It's the sum over all spin configurations of this exponential. Okay, and so some important terms that will come up. So the energy is this sum over edges. So this is the interactions. And it somehow defines the model. This parameter beta is the inverse temperature. And so beta determines how strong the interaction is. So if beta is very strong, then we really care about the this preferring agreement. But if beta is near 0, then we care less about it. And so, right, and so at high temperatures, beta is small, since it's the inverse temperature. and at low temperatures, beta is large. And then perhaps the most important object for us and for statistical physicists will be this partition function. And this is the sum over all configurations of the exponential of the weight. Okay, so these are the basic objects they're working with. And so here's a very, very rough picture of what's going on in a model like the Ising model. And so we have two dramatically different regimes. So high temperature, remember this is small beta. The interactions are weak. And so what do you see? You see some very rapid decay of correlations. So if you look closely at the picture on the left, you'll see that actually if you pick a random vertex, the neighbors tend to agree. There is clumping of the colors. But if I look at a vertex over here and a vertex way over here, they're essentially uncorrelated. If I pick a random vertex over here, it tells you very little about the chance a vertex over here is pink or blue. And so what we would say is that this exhibits long-range disorder. And then there's also some computational things that go along with it. Certain Markov chains mix rapidly in this weak interaction high temperature case. Now on the other hand, low temperatures, so remember this is large beta, so the interaction is very strong. And you see something very different. The correlations really persist on a global scale. And so this Ising model that I defined for you is completely symmetric between +1s and -1s. And so if we see half the time this pink-dominated configuration, we'll also see half the time the blue-dominated configuration. And so what that tells you is if you see that this spin over here is pink, it's actually very likely that this spin very, very far away is also pink. And so this exhibits strong correlations and long-range order. This is a sort of the big picture you should keep in mind, the intuition. And what are statistical physicists interested in? They're interested in, as you vary beta, as you make the interaction stronger or weaker, when do you transition between this high temperature phase to this low temperature phase? And so the idea of that is a phase transition. But that's basically the level at which I'll talk about this intuition today. Okay, so maybe a more combinatorial model in statistical physics is called the hardcore model. And this is a model of, say, a gas. And it's really a model of a random weighted independent set. So a set of vertices that don't span any edges. And okay, what's the probability distribution? You pick an independent set with probability proportional to lambda to the size of the independent set. So lambda is called the fugacity, and it sort of governs how large an independent set you'll typically draw from this model. And so the picture, again, we have Z2. And this is a sample from the hardcore model with large lambda. And what are you seeing here? So the white squares are unoccupied, not part of the independent set. The blue squares are occupied vertices that have an even sum of their coordinates. So white squares on the checkerboard. And the red squares are odd occupied vertices. And so you see that there's some long-range order going on here as well between the even and odd vertices. In this Ising model, there was two configurations that had maximum weight in the probability distribution, the all pink and the all blue. These we'll call ground states. Whereas here in this hardcore model, on this bipartite graph, there's the all even occupied and the all odd occupied ground states. Okay, and please do ask questions in the chat as I go. I don't want to go too fast with this initial stuff. So one thing that you'll see just by the pictures, and there's something to it, is that large lambda is something akin to low temperature, where we really see this low temperature, strong interaction, strong correlation picture that we saw before. Okay, so this is the statistical physics picture. And these two this distribution here that I've defined, the hardcore model, and this hardcore partition function. This is, of course, just the independence polynomial in graph theory. but these will be crucial objects going forward. Let me just note very quickly that if you plug in lambda equals 1, then Z is the number of independent sets of your graph. Okay, so this is some generalization of counting. Okay, so how would I describe the statistical physics perspective to understanding these models? The first is that understanding this partition function is the central task. Oh, okay, good question. So Andre asked a question. Can you say something more about the hardcore model and why does it appear in statistical physics? This is actually my favorite topic. Maybe he knows this, but there's a very simple model of a gas that's basically a random sphere packing in three-dimensional Euclidean space. And so you can imagine just modeling the air in the room as spheres, molecules. The only interaction is that they can't overlap. And so this is actually a random independent set on the graph, the infinite graph of a box in RD with an edge if you're at distance less than 1, say. It turns out it's very, very hard to prove anything about this model. And so the hardcore model is a discretization of this. You can imagine that there's like tilted squares that represent particles, and an independent set on Z2 represents this kind of hardcore gas. So there's a fascinating history about this particular model that I'll skip for now, but that's the background. Okay, so when they want to understand the phase transition, it turns out understanding the partition function, and in particular, how fast does the partition function grow if you take a sequence of graphs tending to some infinite graph. That's somehow the central task in statistical physics. And if you understand that growth rate, you understand all the phase transitions. How do they go about understanding the partition function? They actually start by trying to understand correlations. When do you expect correlation decay? When do you expect strong correlation? Can you condition on some event and get rid of correlations? Questions like this. And in particular, as I mentioned, they care about changes in correlations as the parameters change. So as you increase lambda in the hardcore model, as you increase beta in the Ising model, how do the correlations between spins change? When do long-range correlations emerge? Okay, so in combinatorics, what are we interested in? We're interested in counting. So understanding this partition function is a kind of weighted counting. We're also interested in properties of a typical object in combinatorics, and this is somehow understanding correlations between spins. And then we're often interested just in the unweighted counting problem in combinatorics, but it turns out that having this extra parameter, having the temperature parameter, having the fugacity parameter actually can help quite a lot. And hopefully I'll convince you of that as we go. Good. Okay, so if we had that low temperature picture in statistical physics, what is a low temperature picture in combinatorics? So one typical task in extremal combinatorics is to find the largest object or some sort of extremal object satisfying a certain property. We might also want to count the number of such objects or describe a typical object like that. And there's a translation, there's a dictionary between the physics terminology. So the extremal object, as I mentioned before, this is like the ground state. So on this symmetric bipartite graph, it's quite easy to find the maximum independent set. It's the evens or the all odds. Counting the number of this type of object, well, this is like computing the partition function, and describing the typical object, this is understanding this Gibbs probability distribution. Okay, and so now to some concrete combinatorics. The problem I'll talk about mostly today is independent sets in the hypercube. And so let's see, so QD will just be the discrete hypercube, and we'll consider its independent sets. A very beautiful and very famous result of Korshunov and Sapozhenko from 1983 gave the asymptotics of the number of independent sets of the hypercube. And so the number of independent sets of the hypercube is 2 plus little o1 square root e 2 to the d minus 1. So if anyone saw Jin-Young Park's talk about maximal independent sets in a hypercube on Monday, she explained very nicely where the factor 2, where the factor root e, where this exponential factor comes from. We'll also see where these factors come from today. But maybe even more important than this particular result was a later proof of Sapozhenko of the same result that really proved extremely influential in combinatorics. And this method was an example of the method of graph containers. So finding a small set of containing sets that contain all or most of the independent sets of a graph. And of course, now we have very powerful methods, hypergraph containers, graph containers. But this is somehow why this result, besides being beautiful, is also quite influential. Now, following up, so as I wrote here, the number of independent sets is just evaluating this partition function, hardcore partition function at lambda equals 1. And so Galvin in 2011 made a nice generalization of this result, and he gave the asymptotics for lambda at least 0.4 something, square root 2 minus 1. And just as a sanity check, plug in lambda equals 1 to this formula. The 2 cancels with the 2. You get e to the 1/2, and you get 2 to the d minus 1. And so this is a nice asymptotic formula. And then for a much bigger range of lambda, he gave the asymptotics of the log partition function, but not asymptotics of the partition function. Okay, and so the results in the paper, and here, I'm going to write some big formulas. The formulas aren't important. The results are not even so important. It's going to be the method. But so one of the results we can prove with this method is for any fixed lambda, as small as you like, you get the asymptotics of the partition function. And so here, for example, let's take, instead of lambda greater than root 2 minus 1, lambda greater than the cube root of 2 minus 1. And then what does the formula look like? You have the 2. You have the same term in the exponential that Galvin had. And then you have another lower order term here. And then you have this 1 plus lambda to the 2 to the d minus 1, just like Galvin's formula. And so the idea is the smaller the lambda is, there's still an asymptotic formula for the number of independent sets, but you'll have to see more and more terms in the exponential. And my talk today will explain where these terms come from. So that's one result. Another result, let's say you're just interested in the number of independent sets. Well, we have the formula, the Sapozhenko Korshunov formula here, 2 root e, 2 to the d minus 1, and with the 1 in the parentheses. But then you have the next order term, and so on. And actually, we give an algorithm where you can compute any term, as many terms as you like, of this expansion. So you can get very, very accurate expansions of the number of independent sets. Maybe slightly more interesting would be if you want to understand typical weighted independent sets. So pick an independent set from this hardcore model on the hypercube at different values of lambda. One thing we can get from this method is basically a complete probabilistic understanding. So we can understand of the structure. So Poisson limit, central limit theorems, large deviations, correlation decay. Almost any question you would like to ask about the structure, we can answer, and it follows naturally from this method. But I do want to emphasize, really, it's the method I think you'll find interesting, and hopefully you'll be able to apply it to some problems of your own. Okay, so any questions about the setup? Okay, so now the bulk of the talk, I'll try to explain this method, the cluster expansion method. The cluster expansion is one of a number of tools from statistical physics we would call perturbative. And the idea is that there are some simple structures or simple distributions. Good question from Andre again. Was Galvin the first to use this model in a combinatorial problem? No, so this hardcore model actually, you'll see with a cluster expansion, hardcore model and cluster expansion actually have been used quite a lot in combinatorics. There's going to be a quiz question halfway through the talk, so I won't spoil it. But you'll see a much earlier use of the hardcore model and actually cluster expansion. But very good question. Okay, so a perturbative tool, we start with something we know well, maybe IID spins. or a constant configuration, and we want to measure the deviations from this. Oh, another question. So what is the connection between partition function and the number of independent sets? So the partition function is this sum over all independent sets lambda to the size. If you plug in lambda equals 1, you get the number of independent sets. So Z is supposed to be a Z of 1 is the number of independent sets of G. And so really the partition function is a generalization of the count of independent sets. And that's the crucial thing. Okay, so how can we do this? Let's say we're talking about the easing model. You can imagine at high temperature, things look very disordered. And so if we wanted to measure deviations from something easy and known, you would expand around IID spins. So you would say, how different does this distribution look to the distribution if I just flipped a 50-50 coin, pink, blue for each spin? However, at low temperature, remember what we saw. We saw a huge sea of pink with some blue islands, or alternatively, a huge sea of blue with some pink islands. We would actually want to understand the deviations from the monochromatic state, or in the hardcore case, deviations from the all even occupied or the all odd occupied. Okay, and so that's the idea. We're going to perturb, we're going to understand the system as a perturbation around something quite easy. Mathematically, what this will involve will actually be controlling some infinite series representation of a log partition function. And that's the cluster expansion. Okay, so it's an infinite series representation for a log partition function. That's fine. So two questions you should have. One is, what are the terms? How do you compute the terms of the cluster expansion? What do they represent? And if you're going to try to use this cluster expansion for anything useful, you better hope that this series converges and that you have control on the rate of convergence. And so I'll explain both of those things. And somehow the natural setting for this is a multivariate hardcore model. So I have a graph G with a bunch of vertices, and to each vertex I assign a different fugacity, so lambda V to a vertex V. And now the partition function is just sum over all independent sets, product over vertices in this independent set of lambda V. And so if you set lambda V equals lambda for all V, then you get the usual hardcore model, but this will give us some extra flexibility. Okay, and so what the cluster expansion will be an infinite series representation of log partition function in this multivariate setting. Okay, so a couple of definitions. A cluster will be, I should say, ordered. A cluster will be an ordered set of multi-set of vertices that induce a connected subgraph in the graph. So it might be V1, V1, V1. So we can write that V1, 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 or say V1, V1, V2, if V1 and V2 are connected. If V1 and V3 are not connected in the graph, then V1, V3 is not a cluster because it doesn't induce a connected graph. Okay, a question just came in. Could you remind us of the physical interpretation of these lambdas? They're just a weighting factor. So the larger lambda is, the more likely you are to include this vertex in the independent set. So you can think of it as like a prior. Lambda over 1 plus lambda is the prior probability that you would be in the independent set, but you have to condition on being an independent set. So it controls the density. Okay, so this is a cluster. It's some connected object with repetition. And then there's this combinatorial function called the Ursel function. You know, it's not so important to understand what this is, but I'll describe it anyway. You just think of this as some function of a graph. So use this graph H, and what you want to do is take 1 over the number of vertices of H factorial, and then sum over all spanning and connected edge sets minus 1 to the size of A. So the example I'll give is you have a triangle. H is a triangle. And so what do you have for phi of H? Well, you have 1 over 6, 1 over 3 factorial. And then there's 3 spanning connected edge sets of size 2. Right? So 3 times minus 1 squared. And there's 1 spanning connected edge set of size 3. So if I do the algebra right, this is plus 3 minus 1. So this is 1/3. Okay, so it's just some function of a graph. Very good. Okay, so what is the cluster expansion now? Formally, as a formal power series, log z is the sum over all clusters. You take the cell function of the graph on the cluster. And so there's an edge if there's an edge in the graph, but there's also an edge if it's the same vertex. So you can think of this is the graph in the looped version of G, and then product over V in the cluster, lambda V. And so I'll give one very simple example. So imagine our graph is just a single vertex. So if our graph is just, and here's V, and let's say it has fugacity lambda. So if V is the only vertex in our graph, then the clusters are just 1 copy of V, 2 copies of V, 3 copies of V, and so on. They're just the k tuples of V. And so what are we saying? We're saying log Z equals sum k greater than or equal to 1. Now we're going to multiply for each copy of V, we're going to multiply lambda. We get lambda to the k. And so we saw that the cell function of the triangle, so the complete graph on 3 vertices was 1/3. This generalizes. So I think the formula is -1 to the k plus 1 over k times lambda to the k. Oh, okay. So this is lambda minus lambda squared over 2 plus lambda cubed over 3, and so on. Well, this is just the power series for log 1 plus lambda. And that's 1 plus lambda is the partition function of this single vertex. Okay, so that's a simple example, but it shows you what's going on with the cluster expansion. And notice that even if the graph is a finite graph, this is an infinite series because you can take multiple copies of the same vertex in a cluster. Okay, so now that we know what the cluster expansion is, it's this series with terms corresponding to some sort of connected object. Very important question is, when does this cluster expansion converge? And this is a very old and important topic in statistical physics, dating back to Meyer, Penrose. It's a very important question when this series converges because it allows them to really understand these systems and prove the absence of phase transition. Okay, but here's a very useful theorem of Katutsky and Price on sufficient condition for cluster expansion convergence. Okay, so you're going to have this auxiliary function A from your vertices of this multivariate hardcore model to real numbers. And the condition of the theorem is that for every vertex, if we sum over the neighbors of this vertex and the vertex itself, e to this function times lambda u, and this works even if lambdas are complex numbers. This must be less than a of v. So if this condition holds, it's something about how it's easier to satisfy the smaller the lambdas are. So it's a condition on the smallness of the lambdas. And the conclusion is that if this holds, then the cluster expansion converges absolutely, and you get some bound on the absolute values of the terms of the cluster expansion. Okay, and you can use this to get a good control on the rate of convergence. Okay, so that's the Katutsky-Price theorem. Let me give you one example. And that would be, we have a hardcore model. So someone asked the question. Please don't read the question that was just asked, because this is going to be my quiz question for you. But the answer to the question just asked is yes. So my setting, here's the setting. So G is a graph of max degree delta, and all the lambdas in absolute value are less than some particular value of lambda. And so let's check this condition. So the condition says that we want to sum over all the neighbors of, this sum is at most, so sum over U in the neighborhood plus of V, e to the 1, let's say a of V is 1, e to the 1 times lambda U. Well, this is at most. That's a graph of max degree delta, so there's delta plus 1, at most delta plus 1 terms there. And then we have a E and we have a lambda. And we want this to be less than or equal to 1, right, which is A of V. And so that tells us that lambda less than or equal to 1 over E delta plus 1 suffices. Okay, so my question for you is, does this formula look familiar? Or does this condition look familiar? Yeah, give it a look and see if you've seen this before. And okay, the answer is in the chat, but yeah, this is exactly like a Lovász local lemma condition. And there is a very close connection between the convergence of the cluster expansion and the condition, the optimal conditions for the Lovász local lemma. And so in particular, as Faris mentions in the chat comment, there's a great paper of Shearer and then a very large and interesting paper of Scott and Sokol that really delves deep into this question. And so there is this fascinating connection, and it's exactly this object that we're working with. Okay, good. I'll give some references at the end if you want to follow up for more. I think what's interesting is that we can also use the cluster expansion at low temperature. And so perhaps this is what is new in this method. Previous combinatorial applications of the cluster expansion usually were in this high temperature, small lambda regime. But a lot of combinatorics is somehow at the other end. It's at this low temperature regime where we're near the ground state. And so what do I mean here? So how can we use the cluster expansion to account for deviations for ground state? And what do I mean? So for the Ising model, the deviations from, say, the all blue ground state, we could call these connected components of red vertices. Okay, and so somehow we want to understand how those interact and quantify the contribution to the partition function from these small deviations. But for independent sets in a bipartite graph, the deviations are a little bit different. Okay, so what we said is, let's say we have this bipartite graph, n over 2 vertices on each. There's 2 ground states, right? The even ground state, or we could say the no odd ground state, and the odd ground state meaning no even occupied vertex. And each of these has weight 1 plus lambda to the n over 2, right? Because if I have no odd vertices, then for each of the even vertices, I can choose whether to put it in or not. There's no edges between it, and so we get a weight 1 plus lambda to the n over 2, or if we're in the unweighted case, 2 to the n over 2 independent sets that have no odd vertices. Okay, and we think of these as the ground states. So the ground states are kind of like collections of independent sets with no defects, no vertices on the wrong side. But what are deviations? Deviations from this all even set of independent sets would be independent sets with occupied vertices on the wrong side. And so, you know, maybe we have 1 occupied vertex here, maybe there's 2 occupied vertices here. And the definition I'll use is that a particular deviation is a 2-linked component of odd vertices. So 2-linked meaning connected at distance 2 in the original graph. And so here we have 1 deviation here and 1 deviation here. And then what we want to ask is, how much does this deviation cost us relative to the ground state? Okay, well, you know, each deviation, well, we add a factor lambda from having this vertex in the independent set. But we lose, when we go back to the evens and try to add all the vertices in, some of them are blocked. And so a deviation costs us lambda to the number of vertices in the deviation divided by 1 plus lambda to the size of the neighborhood on the even side. Okay. And so, this will tell you how many independent sets are there with exactly these vertices occupied on the odd side. The very, very important fact is that this cost factorizes over the deviations. So by the way I define deviations, that it's two linked, we know that the neighborhoods of different deviations don't overlap. And so the cost of a collection of deviations is the product of the cost of the single deviations. This actually will allow us to rewrite these partition functions. Okay, so we want to rewrite the partition function in terms of deviations, which I'll now call polymers. That's the word from statistical physics. And we can write it like this. The independence polynomial is 1 plus lambda to the n over 2. Now sum over all collections of compatible polymers. Compatible meaning their union is not too linked, they don't overlap. And then product over the polymers in this collection of this weight, the penalty. So this, this is the factor for the ground state, and then you sum over a bunch of things, including the empty configuration. That will correspond to the ground state, but you also sum over all the deviations. So this looks quite nice. This is actually an exact formula, and it's not quite helpful because we wanted to measure contributions from mostly even or mostly odd configurations. If we're judging our intuition correctly, that most independent sets are mostly even or mostly odd, and so we want to measure these separately. And so the only change we'll make is we'll say that polymers now are defects, but of size at most, say, n over 10. Okay, so we're insisting that they're small deviations in a very weak sense. And now we can define the even partition function as 1 plus lambda to the n over 2 times some new partition function that we'll call psi even. And psi even is just this sum over collections of compatible small polymers of odd occupied vertices, product of the weights. Okay, and so just stare at this a second. It's a sum over collections of things, and the condition on the collection is they must be disjoint, they must not be connected, and then a product over things. And so this is exactly a multivariate hardcore model again. But it's a hardcore model where the vertices are now polymers. They're collections of our original vertices. But we can use all the machinery of this cluster expansion now in this other setting. And so what have we gained by defining these new partition functions? And it really depends on the graph and the value of lambda. Actually, let's go back 1 second. And a very important thing to note is, we wanted small values of lambda for this cluster expansion to converge. The way we've defined the cost function, the larger lambda is now, the smaller the cost. So we've completely switched perspectives, where large lambda now means small weights in this new generalized hardcore model. Okay, so what have we gained? Depends on the graph, and what we'll see is that if G is a sufficiently good expander, okay, and lambda is large enough, then we have this nice representation of the original partition function. It's approximately the sum of the even and the odd partition function that we get. And then, moreover, we can really understand Z even and Z odd by applying the cluster expansion to psi even and psi odd. And so that will be the idea. Okay, and cluster expansion convergence is great. It allows us to approximate Z. You can even do this algorithmically, but it also gives a lot more. It gives a lot of correlation decay properties, any probabilistic information you want to know, really you can read off from a convergent cluster expansion. Okay, so what I'll do for the rest of the time, I'll show you how to implement this. The first warm-up example will be something like a expander graph, a delta regular expander graph. And this is based on a joint paper with Matthew Jenssen and Peter Kivash, where we were interested in algorithms for approximating the independence polynomial. And then I'll get back to the the topic I started with, independent sets in a hypercube. Of course, the hypercube in general is not a great expander for large sets, but this is where actually this method of graph containers will help us. And so that somehow will be the punchline by the end, that you can, the key ingredient you need to apply the cluster expansion is actually given by the method of graph containers. Okay, so expander graphs, let's say G is a delta regular bipartite graph, n vertices, so n over 2 on each side. And what do I mean by expanding bipartite graph? I mean that, say, the neighborhood of a set that's just on one side of the partition is at least 1 plus alpha times the size for some positive alpha, and let's say for every set S that's at most half of the vertices. So at most a quarter of the size of the full set. Okay, and so again, it's a bipartite graph, a balanced bipartite graph. So we have this same cost function for these deviations, these polymers, and we'll call this the weight of gamma for a polymer gamma. And what we want to understand is this even partition function, psi even, sum over all compatible collections of deviations of polymers, product of weights. And again, as I said, this is really just a multivariate hardcore model with the incompatibility graph of polymers being the underlying graph. So two polymers are joined if you take their union, this is two linked. Okay, and as I said, the larger the lambda is, the smaller these generalized fugacities. And so we can hope to, now we somehow switched from low temperature to high temperature. Okay, so let's check the Katetsky price condition. Okay, we can do this. So the point we'll use is the following. We'll use the fact that, let's see if I have this, expansion gives us a bound on the weight. So expand, yeah.
There is a question.
Oh, good, good. Yeah, so can you explain the intuition for this gamma function? Yeah, so let's do the drawing. So remember, the ground state we're thinking about is you pick all the vertices on the left, the even vertices. You pick them, you can have them in or have them out, and that gives you 1 plus lambda to the n over 2. But now if I tell you here that this vertex, I want to insist that this vertex on the right is included, well, that gives me a factor lambda because I'm including one vertex. But I just blocked, I killed all the neighborhood of this vertex. And so, it gains me a factor lambda, but I lose a factor 1 plus lambda to the size of the neighborhood if I want to sum over all independent sets that have that vertex occupied on the right. Okay. So the point is that we're not comparing it to a single independent set, we're comparing it to a whole family of 2 to the n over 2 independent sets in this collection of independent sets. And so you get a penalty because while you added that vertex, you just lost the choice you had over many other vertices. So that's the intuition. Okay, so expansion gives us some bound, right? Because expansion is saying that the neighborhood is large. It's at least 1 plus alpha times the size. And so now we have a bound just as an exponential in the size of lambda. I don't want to waste too much time on the calculation, but the calculation comes down to something like this. We want to sum k at least 1. So how many 2 linked components are there containing a certain vertex? Well, it's something like e delta squared to the k. We're trying to balance the contributions from all polymers of size k in the Katetsky price condition. We have like e to the k, and then we have let's say lambda over 1 plus lambda. Oops, let me say lambda to the k over 1 plus lambda to the 1 plus alpha k. And so I won't go through this calculation, but you can see that if alpha is large enough and lambda is large enough, this exponential on the bottom will kill the rest of the exponentials. And so this will converge and be small, let's say small, if alpha is greater than 0 and lambda is large enough. So if you want to see this calculation in more detail, I'm happy to do this after the talk. But the point is that we can show the Katetsky price condition holds, and this gives us convergent cluster expansion. We're not quite done though, because what that tells us is something about how do you approximate z odd or z even. The other important thing to understand is that really that's all there is. And so we want to say that if you subtract z odd and z even from z, this is very small relatively to the whole partition function. And what's interesting is this is actually like a type of result that people prove all the time. This is a slow mixing result for a Markov chain. It says there's some exponential bottleneck in the state space. And so then the algorithm, if you want to approximate the number of independent sets in this expander graph, you would compute the cluster expansion up to some number of terms for psi even and psi odd, exponentiate them, add them together, multiply by 1 plus lambda to the n over 2, and that gives you your approximation. And so it turns out this is quite accurate. Okay, so back to the hypercube. So one good thing about the hypercube is that small sets expand quite well. Say sets of size at most d squared expand by some constant times d. And so we can use the same argument that we did with expanders, but large sets don't expand well. So, sets of size, say n over 4, they might expand by a factor 1 plus 1 over root d. And so using the same argument, we would need very, very large lambda. And we're interested in lambda equals 1, lambda equals 1 over 10, lambda going to 0 as d goes to infinity. And so this is actually where the container lemma comes to the rescue. And so, you may or may not have seen container lemmas before, but here's the one for the hypercube. And this is due to Sapozhenko, but also Galvin for the weighted case. So there's some family of two-link components in the hypercube on one side. And these are ones whose, let's say, their size is A. It's not quite the size, but close enough. And their neighborhood size is B. And then this container lemma is exactly the type of thing we need. So this is the weight function, right? This is the weight of a polymer A. If you sum over all of these, this is at most 2 to the d times some exponential. But if B minus A is large, this is small. And there, B minus A actually has to be relatively large because of even the weak expansion in the hypercube. But the point is that this is actually, this works perfectly to verify the Katetsky price condition in the hypercube for large polymers. And so, literally the condition you need was already given by Sapozhenko and Galvin. And so now you can ask, if you have cluster expansion convergence and this kind of bottleneck approximation lemma, what can you do? So the first thing is that you know that the partition function is up to some exponentially small error. It's 2 for the even and odd sides, 1 plus lambda to the 2 to the d minus 1 for the ground state, times the value of this polymer model partition function. And here, because of the symmetry of the hypercube, we can just say 2 times psi even. Okay, so that tells you something about the partition function, but it also tells you how to approximate the hardcore model, the random distribution. And this is what I meant by you can read off most probabilistic information. Here's a very, very good approximation to the hardcore distribution. Pick a side, even or odd, with 50-50 chance. Sample a random configuration of polymers with probability of compatible polymers, so of defects that don't overlap, with weight given according to this polymer model partition function. And so then what do you get? You've picked your side, you've picked some deviations, these are too linked or whatever. They block some vertices over here. And then with the remaining vertices on the left, you just independently with probability lambda over 1 plus lambda include them or not. And so this is a very simple probability measure, especially because this generalized hardcore model has exponential decay of correlations and all the nice properties you'd like. But it turns out this is very, very close to the true distribution. So this is how you read off probabilistic information. Okay, so I can show you, maybe this will be the last thing I tell you. I can show you what are the terms that you get in the cluster expansion. And so the theorem is that the partition function on the hypercube is this factor out front times the exponential of some sum, and the LJs just depend on clusters of size at most j. And then the error term is of lower order than the last term in this series. So you can truncate this wherever you like and get an approximation with guaranteed error bounds in the exponent. And so if you want a asymptotic formula for z, you just want to make sure you go out, you choose k large enough so epsilon k tends to 0 with d. So what do the terms look like? Maybe I'll just give you the first term. There's just one type of polymer of size 1. There's 2 to the d minus 1 of them for every vertex, every odd vertex. Its weight is lambda over 1 plus lambda to the d. Okay, and so if you sum over clusters of size 1, you get something like 2 to the d minus 1 lambda over 1 plus lambda to the d. And this is exactly the term that the first term in Galvin's formula. Okay. And then if you want to go further, you have to look at, let's say, polymers of size 2. So these are 2 vertices on the left that share a common neighbor. I think there's something like 2 to the d minus 3 times d times z minus 1 of them. And their weight is something like lambda squared over 1 plus lambda to the 2d minus 2. And it's by using these things, computing Ursel functions, that you actually compute these higher order terms of the expansion. Okay, so I'll skip over this. This is describing what sort of probabilistic information you can understand. I'll skip this. Let me just mention some further applications of this method. So Bala, Garcia, and Lee recently posted a paper that gives the asymptotics for the number of independent sets in the middle 2 layers of the hypercube. What's interesting here is that by using this method, they were able to obtain the asymptotics because the asymptotics, unlike the number of independent sets in the hypercube, it uses 2 terms of the cluster expansion. And so their formula has exponential something plus something, but it really is just the first 2 terms of the cluster expansion. Matthew and Peter Kivash recently obtained the asymptotics of the number of Q colorings of the hypercube. So previously Galvin for Q equals 3 and Jeff Kahn and Jinyun Park had done 4. These 2 results just use 1 term of the cluster expansion. For higher Q, you need more terms. And so their formula, depending on what Q is, uses various numbers of terms of the cluster expansion. But it falls very naturally from the cluster expansion. Another application that we recently did was we proved something called the upper matching conjecture for large graphs. And there we used the cluster expansion, but for the number of independent sets of a fixed size. And this was more of like a high temperature cluster expansion, but it was enough for what we needed. And then there's many new algorithmic results at low temperature. So how can you approximate partition functions and sample from models in the strong interaction regime where, say, Glauber dynamics, a local Markov chain mix is slow. Okay, so I included the link to the slides in the chat, and so you can click on these links if you download that PDF. the paper I talked about, a nice exposition of Galvin on the container method, a really, really good book on statistical physics. I recommend this to everyone that asks me, Friedli and Villanik, and it's freely available on their website. Also a nice physical book. Scott and Sokol, someone mentioned this in the chat. And then there's a paper there if you're interested in the algorithmic applications. There's a paper link there. And I'll let's see, some open problems. Of course, like one obvious open problem is whenever you use graph containers, can you get something sharper or get more information by combining it with the cluster expansion? More ambitious problem is how do you combine the cluster expansion with hypergraph containers? And then very open problem that I'm thinking about all the time is what are some other applications of statistical physics tools to combinatorics, computer science, other areas. Okay, thank you, that's it.
Thank you very much, Will, for this really interesting exposition. Are there any questions on what Will have talked so far?
Yeah, maybe I have a question if I could ask one. Can you hear me?
Yeah. Yeah.
Hi, Will. That's a really beautiful talk. This may be a very naive question. It's just about when you had the approximation to mu in terms of sampling a configuration of polymers.
Yes.
So superficially, that looks very like if you have, for example, low temperature Ising model or something on the square lattice, you can represent a configuration by a collection of contours, and you can effectively sample a population of contours in a non-overlapping way, and that's the same. Is that? I mean, that feels similar, but it also feels much simpler. I don't know if those are genuinely related or not.
I think what I'm doing is actually much more simple than the contour representation. So it certainly comes from that, and this contour representation for low temperatures is actually where all this stuff comes from. It turns out contours are more tricky because you have to define things inductively, because you could have a contour and then another contour inside the contour, and so on. So that situation is more complicated than this, where here we have, because we have such strong expansion, you don't have to worry about things inside.
Okay.
But all of this stuff works with contours. And so I think the link I have to the algorithmic paper, the first time we applied this was to algorithmic problems for, say, hardcore or POTS contour models. So it all works out. It would be interesting if there was a combinatorial application of contour models as opposed to polymer models. That would be interesting to find.
Okay, thanks.
Well, someone asked the question, have these methods been applied to counting graph homomorphisms generally?
So I think, yeah, so certainly this paper of Matthew and Peter Kivash, I think they deal in a lot of generality there. So certainly for the hypercube, that's one example. And then another example is there's a recent paper of, I know, Andreas Galanis, Leslie Goldberg, James Stewart. I think those are the three authors. So just posted in the last week or so. And they're interested in algorithms for counting homomorphisms in bipartite expander graphs. And they can do this in complete generality. So if the degree of the expander graph is large enough, then they have an efficient algorithm to count homomorphisms. So it all works.
Great. Okay, I would actually be, I mean, if you don't mind sharing some more of the details.
Yeah, so should we take like a 5-minute break? I'll get a glass of water. Everyone can, I guess it's very easy virtually to leave without being noticed. But yeah, so anyone that wants like some more technical details, and I'll work through it slowly, is free to stay, but everyone else can go on and enjoy their day inside. But yeah, so should we like meet back in like at, I don't know what time it is everywhere, but at 10 after the hour, whatever hour that is?
Yeah, I think that's a good idea.
Okay, great.
Okay, so let's meet in 5 minutes at 10.
Yeah, very good.
Something, yeah.
Okay, thanks everyone for attending. That was fun.
Thanks a lot. Well.
So are there particular things you would like me to go over in more detail, or just sort of go through the general thing, the details more slowly?
Well, there is one particular thing that I was interested in, definitely, is this kind of particular technical thing is, you said that one thing that we need to show is that there is nothing else. There's just odd and even regime, right?
Yeah.
This kind of thing. It is not, I think, it should not be a big deal in general, as far as I understand, but it would be interesting to see the details still.
Yeah, so, right. So the idea there is basically you can just use expansion. So let me write this here. So how to show to show the bottleneck. And it depends on the particular model. Sometimes just expansion is enough. So let's say you're in a bipartite expander graph, and what do I have to really bound? I have to say, I either expect there to be a lot of independent sets. I expect most of the occupied vertices to be on the left or on the right. But imagine I told you that I have a big set on the left and a big set on the right that are both occupied. Depending on the expansion, if it expands quite a lot, both sets expand quite a lot, you'll reach a contradiction. And the sum of like the neighborhoods and the things is bigger than the size of the graph. So in that example, it's quite easy. In the hypercube, it's a bit harder, but there's a paper by David Galvin and Prasad Tedali. It's about slow mixing for Markov chains for hardcore on the hypercube, but also in general, much more general. It just uses expansion, but expansion at different levels. And so I guess that's kind of the one interesting thing is that the starting point for these tools, if you're going to make this low temperature stuff work, the starting point would be to be able to prove a slow mixing result. And a slow mixing result really is saying that the state space, the set of all independent sets, looks something like this, that there's this exponentially small bottleneck between. What you get extra out of the convergent cluster expansion is a statement of the fact that there's no other bottlenecks, okay? Because, in theory, if you find one bottleneck, it could be that this part of the state space has another bottleneck. But by saying that the cluster expansion for this restricted part of this restricted partition function has a convergent cluster expansion, it really means there's no bottleneck. And there's lots of ways to state that formally. One would be that I don't know, the correlations can decay exponentially fast if you restrict your configuration to this side or this side. So it's the method is something like slow mixing plus something else. Slow mixing plus no slow mixing at any other scale.
Oh, great. And this, when you say slow mixing, it's you literally refer to a walk on a graph of independent sets.
Yeah, so the Glauber dynamics, let me write this, it's interesting. So it's a Markov chain on the set of independent sets of a graph. Glauber dynamics for independent sets. And what do? You pick a vertex at random. Then with probability lambda over 1 plus lambda, try to add this vertex to the current independent set. and with probability 1 over 1 plus lambda. Remove V if it's in the independent set. Okay, and these two probabilities you do exclusively. And so this defines some random walk on the set of independent sets of a graph, and it converges. The stationary distribution is the hardcore measure, but the question is how quickly does it converge? And if you find a set of independent sets that has exponentially small weight and separates two sets that have weight 1/10 each, then that's enough to show that this takes exponential time to mix. It's going to take a long time to get from an independent set on the left to an independent set on the right.
Oh, yeah. Cool. There is a question in the chat. How can we interpret the typical structures from this counting formula?
Okay, good. Great question. And so let's remember what the formula looked like. So let's say Z of 1 was something like 2 times square root E times 2 to the 2 to the D minus 1, right? So this is the Sapozhenko formula. And so let's remember where the factors came from. So 2 is from even odd. 2 to the 2 to the D minus 1 was for the number of independent sets in the ground state. So the number of independent sets, say, with no odd vertex. And now the square root of E, this was X of L1 in the cluster expansion. And so remember what L1 was. It just took into account vertices, single vertices, isolated vertices that were occupied on the right. And so what this is saying is that, this is saying that the contribution, so if you just looked at the ground state, you would get 2 times 2 to the D minus 1. And what this is saying is you're actually getting a factor root E from independent sets that have just single, some number of these single vertex defects. Okay, and so actually what you can read off, and Galvin did this already, just from this formula, is that if lambda equals 1, then the number of defects, polymers of size 1 is Poisson with mean 1/2, I think. And so the way to interpret the, you'll see in the expansion, you'll see contributions at different orders in the cluster expansion, and you can really somehow, and there's some pretty automatic ways to do this, but you can really read off the contribution from different types of polymers. And so, why, when we had lambda is at least 2 to the 1/3 minus 1, we had 2 terms of the cluster expansion that gave the asymptotic formula. And what that's saying is actually you need to account for defects of size 1 and of size 2. And you can actually read off the distribution. You can compute all the moments of the number of these defects and things like this. So yeah, in the paper we show how to do this, and the idea is you can compute the cumulants. So cumulant, if you don't know what a cumulant is, I didn't know what a cumulant was before working on this. It's like a moment of a random variable, but scaled in a different way. And so you can compute cumulants of counts of polymers of different types. Via modifications of the cluster expansion. So I see a question in the chat. It's, is that expansion via cumulants terms exact, or is there some errors? You can get, okay, so I think I understand the question. So let's say you want to know the cumulants of the number of polymers of size 1. It's an exact formula, but it's an infinite series. But the point is that you can truncate it, depending on what lambda is, you can truncate it and get almost all the contribution. So that's one comment there. And then there are certainly expansions for different interactions. This polymer model is fairly general, but you can also have, you can turn lots of different spin models into this type of polymer model. In some sense, like this generalized hardcore model is universal. Okay, good.
Can I have one more question?
Yeah, of course.
Yeah, just continue to that L2. So for L1, it's pretty clear, like this corresponds to the polymers of size 1. But for L2, because in the definition, you would have ordered polymers with repetition. So how would you interpret this?
Yeah, so that's a good question. Why don't we just actually compute L2? So I think I sort of did the calculation for L1, right? So, you know, there's one type of polymer of size 1. It's just an isolated vertex. There's 2 to the d-1 of them. And their weight is lambda over 1 plus lambda to the d. Okay, and if you're talking about clusters of size 1, this is all you need to worry about. It turns out there's also one type of polymer of size 2. So as I mentioned, this looks like 2 vertices on the right that share a common neighbor. They actually share 2 common neighbors on the left. And if you do the calculation, there are 2 to the d-3 of them. So basically you say there's 2 to the d-1 vertices on the right. There's d choose 2 ways to pick a neighbor at distance 2, but then we've double counted by 1. So that's how you get 2 to the d-3 times d-1. That's the number of them. And what's their weight? Their weight, well, you have 2 vertices, so it's lambda squared. And then how many neighbors, what's the size of their neighborhood? They each have d neighbors, but 2 of them overlap. And so the weight is 1 plus lambda to the 2d-2. Okay, so that's
minus 1, you mean?
no, because there's like think the all 0 vector on the hypercube, and a generic distance 2 neighbor is 1, 1, 0, 0, 0. And so actually there's 2 neighbors that they share, right? There's 1, 0, 0. Yeah. And so that's where you get the -2 from. Okay, so, but these are just polymers. And so now, you know, L2, to calculate L2, you need to look at clusters of size 2. Okay, and there's 2 types of clusters of size 2. There's 2 copies of the let's give a name to this polymer. Polymer of size 1 we'll call gamma 1, and polymer of size 2 we'll call gamma 2. And so you can have a cluster of size 1 would be gamma 1, gamma 2, but they need to be either the same polymer or at distance, you know, or 2 linked. And then on the other hand, you can have just 1 copy of a gamma 2. Okay. And now, so so here I'm putting an edge to indicate that these are incompatible. And so this Ursel function for this is just, the graph here is just an edge. So this would be -1/2. And then the Ursel function here would be 1. Okay, and so then you have to write out the terms. And so what do we have? Yeah, go ahead.
Yeah, so for the RSL function, we want to count connected components and like count them on the connected components kind of, and like connected graphs, and you put an edge if between two polymers if they're not like if they're
yeah, not compatible.
So
yeah.
meaning that none of the vertices are too linked.
So
Right?
if your polymers are of size 1, yeah, right? Then
they shouldn't.
Here's a vertex. They should either be the same vertex, then they would be incompatible.
Yeah.
If it's 2 copies of the same vertex, or if they are at distance 2. Because they're not compatible, because if, yeah. Okay, so what's the contribution there? So let's write out all these contributions. The contribution is something like, well, there's, so how many clusters of size 2 with 2 polymers of size 1 are there? There are 2 to the d minus 1 times 2 to the d minus 1 plus d choose 2. Sorry, 2 to the d minus 1 times 1 plus d choose 2. Okay, now we have the minus 1/2 factor from the RSL function, and we have to multiply together their weight functions. So we get like lambda squared over 1 plus lambda to the 2d. Now on the other hand, we have plus. Now we have to consider the cluster that's a single polymer of size 2, and that we know already. It's 2 to the d minus 3. D times d minus 1 times lambda squared over 1 plus lambda to the 2d minus 2. So, you get some contribution from the second term from these polymers that made up the first term, but then you also get this new term that corresponds to polymers of size 2. So, I mean, it's not so pretty to see, but it's not hard. There's a simple algorithm for enumerating these things.
So then can we say, let's say the dominating term is L1 plus L2, then can I say typically on the one side, the independent side would have like polymers of size at most 2, or I should say the 2 linked components?
Yes, a very good question, and it's easy to see why that's true. So here's why that's true. You can look at, let's say, just look at the polymer models, and let's say we define 2 polymer models now. One is Z even, and one is Z even less than or equal to 2. Okay, and if just the first 2 terms, and what I mean by this is it's a polymer model, but only includes polymers of size at most 2. Okay, but what we're saying is that Z even minus Z less than or equal to 2 even equals little o of Z even. Right, so that's what it means if L1 plus L2, if anything higher is little o1. It means, right, that what you get by including polymers of higher order actually is negligible. And so what that means is the configurations that have polymers of size at least 3 appear with probability little o1. So it implies with high probability in the random polymer model, all polymers have size at most 2. Okay, but in fact, like this, so this you don't need. you can actually see this just from a simpler first moment argument. Let me see if I have the slide. So David Galvin proved this, in fact. So, right, here we go. So what he proved is he proved this Poisson law for lambda near 1 for components of size 1. But he also proved exactly what you're asking, which is as you cross certain thresholds, or if lambda is at least a certain threshold, then with high probability you won't see two linked components on the wrong side of a certain size. Okay, and that's really just by measuring the contribution to the partition function of configurations with these defects and showing that it's smaller order than the partition function. What we did in addition was to actually characterize the distribution of these components when they emerged and their joint distribution. But from the cluster expansion, that's quite easy because you can compute, say, cumulants, joint cumulants, and things like that.
Okay, thank you very much.
Yeah, thanks for the question.
Maybe I have maybe one more question about the intuition for this Kotetzky price. What is this
Kotetzky price?
Price for the criterion for the convergence. So can you give some intuition on how to how to work with this formula, kind of?
Yeah, so it really depends on like how accurate you want to be. So let's look at the criteria. I mean, basically what it says is that you want to have your weights decaying exponentially in their size, right? Because when you look at this, oops.
You went too far, I think.
Yeah. Okay, here we go. Yeah, and so, if you imagine in this polymer model representation, you think of a single vertex and just all the polymers that can contain that vertex. Certainly those polymers will be incompatible, so they have to be in their sum. And if you're talking about small subgraphs of a delta regular graph, there's something like delta to the k subgraphs of size k containing a vertex. And so if you organize this sum here by the size of the polymer, it's going to be sum over k delta to the k times this weight. And so certainly you're going to need this weight to decay exponentially fast in the size. And then it's just a matter of balancing things out so that and the exact exponential decay rate, that's something that's very interesting and you can try to do better and better. But in general, what you want to say is that if you have some notion of size for your polymer model, that you can show that polymer weights decay exponentially fast. And so, for example, that's what we did with the expanders, right? The expansion condition, let's see. Right, the expansion condition here, what happens there? It tells you that you have actually some constant times the size extra 1 plus lambda in the denominator.
Yeah.
And so that's sort of the whole game, is to find some representation where you can show that these polymer weights are decaying exponentially in the size. And often it's very natural. If you define your ground states and your deviations in the right way.
Okay, yeah, that's really interesting. I don't know if there are any more questions. I think we have asked you quite a few already.
Yeah, let me just encourage anyone that has follow-up questions or wants to do some extra reading on this or learn about it. Please just email me. I have lots of references. I can, if you're interested in some problems, I can discuss with you. So please just do email me and I can give you tips, pointers to this stuff. I think there's lots and lots of ways you could use this. I know Lena Lee, who asked a couple of questions, already has a paper using this, so she would also know. But there should be lots of applications.
Mm-hmm. Yeah, that's great, and it was a great talk, Will. Thanks a lot. Really interesting. A very good format, actually.
Okay, great. Well, thank you all for participating, and yeah, please do email me if you have any questions. I quite enjoyed that.
Cool. Thank you, and hope to see you soon. Bye-bye.
Yes, yeah, in person, right?
Yeah,
okay.
yeah.
Okay, bye,
so.
bye everyone.